Our next speaker is Will Oliver. Will is a professor in the Department of Physics here at MIT and also the Department of Electrical Engineering and Computer Science. He is also the director of the Center for Quantum Engineering. So let's hear it for Will.
Well, good morning. Thanks a lot for the invitation to speak today, and really happy to be here. I'm going to give an overview of quantum computing, I guess quantum computing 101, foundations, frontiers, future impact, and I would welcome your questions. So, let's make it somewhat conversational. Before we get into quantum computing, quantum technology generally addresses three primary topics: the sensing of information, the networking or communication of that information from one place to another, and then finally the processing of that information. And if we had to give it a definition, what is quantum technology as opposed to just technology, or classical technology as we would call it? Quantum utilizes quantum mechanics at a fundamental level to do the sensing, the communicating, and the processing. And we use it because it can do it in ways that are either practically prohibitive or even impossible to do with our current techniques. So quantum enables that. Okay, and that's why we want to do it. Before we get into quantum, though, I would like to talk about the last century of classical electronic computing. And because, as you know, this quote from Mark Twain, right? History doesn't repeat itself, but it does often rhyme. And I think that we can learn a lot from this last century. So I won't spend too much time on this, but classical electronic computing started with the vacuum tube in 1906. It was used for radio transceivers for about 40 years, 4 decades, before it was finally used in a computer called ENIAC that I'm sure we've all heard of, developed at the University of Pennsylvania. The following year, the transistor was invented in 1947, but it wasn't until the 50s that we had a fully transistor-based computer built here at MIT called TX0. But it didn't look like the computers we have today. It was basically these transistors soldered together to make the computer. To get to what we have today, we needed first the integrated circuit. That was the late 50s. But even with that, it wasn't until the 70s that we could actually identify a chip, the Intel 4004 4-bit processor, that we would look at and say, oh yeah, that's an IC, an integrated circuit. Even with that, it wasn't until the 90s that we had the Pentium Pro. I remember using Pentium Pro, maybe some of you do too. 5 million transistors, and at the time that was fantastic. And advanced 30 years now to where we are. We have GPUs, TPUs, of course CPUs still, XPUs, all sorts of processing units. And if you look at the latest Grace Hopper, all right, from NVIDIA, it's 200 billion transistors on the chip. It's amazing, right? 2 chips, each one has 100 billion transistors. And so you think, wow, we're in a good place today, but it took us 100 years to get here. That's the point. Okay. Why did I start with that history? Well, because quantum computing isn't yet 100 years old. It's actually quite nascent. It's recent. In the early 80s, people said, look, if you want to simulate a quantum system, maybe we should use another quantum system to do that, because quantum has a lot of degrees of freedom, and it's hard to simulate. It was hard then, it's still hard today. By the 90s, people started figuring out what you could do with a quantum computer theoretically. For example, Shor's algorithm attacks RSA crypto systems. We care a lot about that, secure communication. But there are many other applications. We'll talk about those. Many of them developed in the 90s, still being developed today. By 2000, we knew, okay, if we could build a quantum computer, it will change the world. And for the last 25 years, people like myself and others, I'm a hardware guy, we're trying to build these quantum computers. Okay. So the takeaway is the following. Quantum computing's real. It's transitioning from a scientific curiosity to a technical reality that's happening right now. But the history lesson here is that advancing from discovery to useful machines takes time, it takes engineering. It's not going to happen overnight. But who here would not have wished that they or their parents had invested in semiconductor technology in the 50s and 60s, right? And look at where we are today. All right. That means you've got to be in the game to play. Right, and so that getting in the game is happening right now with quantum. There's a lot going on worldwide. I won't read everything on here, but a lot of government investment, primarily for the national security aspects and the economic security aspects of quantum. But what's really changed over the last 10 years, I would say, is the number of companies that are engaging in quantum. A few of them here are building quantum computers. Most of them here are the picks and shovels that are going to go into enabling quantum computers to be built. And then several of them are figuring out how to use quantum computers. And we have an industry membership group with our Center for Quantum Engineering where companies come and work with us to figure out how quantum is going to affect their bottom line in the future. And if you'd like to learn more, feel free to reach out to me on that topic. Qubits, quantum bits, the fundamental logic element of a quantum computer. They come in two flavors, natural atoms and then what we call artificial atoms. Natural atoms we all know because we know the periodic table of elements. We pick an element, an atom, it has energy levels and electrons, and we use those energy levels and those electrons to represent quantum information. Okay, so those are the natural atomic systems. Trapped ions, neutral atoms are examples. But we can also build electrical circuits from inductors, capacitors, and junctions, Josephson junctions, and assemble them into what looks like a resonator. And it also has discrete energy levels, and in many ways looks like and behaves like an atom, even though it comprises Avogadro's number worth of atoms inside. So we're not using the atoms there, we're using the circuit, which itself behaves like an atom. And there's actually a whole Mendeleev table of circuits that we can design that'll afford us this property. So quantum computers are built from natural atoms that nature gives us, of course, or artificial atoms, circuits that we build that mimic that behavior. Okay, 2 slides. How is a quantum computer different? One, we can do a compare and contrast with a classical computer. Classical computers are transistors, a bit. It's either on or it's off. Current's flowing or it's not flowing. It's like a faucet. We represent this as a 0 or a 1. Okay, now it's digital. Discrete states, and if you measure that transistor, you will find it in the state you set it in. Transistors are almost perfect. So it's a discrete measurement, deterministic. Qubits are also 2-level systems, this state or this state. You pick 2 of them, and that's your qubit. But the difference is that it's quantum mechanical. And the way that we think about it is you think about it as the planet Earth. At the North Pole is state 0, and at the South Pole is state 1. Now, if you're a classical transistor, you're either at the North Pole or the South Pole. That's your whole world. That's all you know. But a qubit, of course, it can be classical. It can be at the North Pole or the South Pole. But it can also be in what's called a superposition of states, 0 and 1 simultaneously. And when it's anywhere other than the North or South Pole, it's in some combination of 0 and 1. Now, you're standing at a single place on Earth. It's a single state. It's a single state that carries aspects of both 0 and 1 simultaneously. Right? So that's weird. It's quantum mechanics, but that's the way it works. One consequence, though, is if you make a measurement, you'll get a statistical or probabilistic outcome. So if I'm on the equator, I'm half 0 and half 1. I'm in a superposition state of 0 and 1. But if I make a measurement, I'm instantly going to go to the North Pole. Oh, I'm state 0. Or I'm instantly going to go to the South Pole. I'm state 1. It's just like flipping a coin, 50-50, which one you get. It might seem, okay, that's odd. How can I possibly do something useful with that? Well, yeah, it's true. Encoding information in a quantum computer is different. It's part of why it can be powerful. To give an idea of that power, let's consider this. In a classical computer, if you have a number n transistors, okay, you can form an exponentially large number of states, 2 to the nth power. Okay, that sounds great, except you can only represent 1 at a time. So for example, if you have 3 transistors, 2 to the 3rd power is 8. I can represent 0, 0, 0, they're all in zeros, 1, 1, 1, all ones, and every permutation in between. There are 8 of them, but I can only represent 1 at a time. So if for some reason I wanted to calculate an output based on every input, I've got 2 choices. I can either take one computer and feed in 1 at a time those states and get the outputs an exponentially large number of times. I'm going to be doing this for a long time. Or I can buy a very large number of computers and try to do it in parallel. All right, but either way, it's going to take exponential time or exponential hardware to do that task. Now, a quantum computer, on the other hand, okay, same. Now you have n qubits, 2 to the n classical states, north and south pole for each one, but you can put them all in superposition. So you form one state, 000 plus 001 plus all the way up to 111. And you represent all of them in that state. And what this affords you is something called quantum version of parallelism. And it leverages quantum interference to do calculations. Now, we haven't made a measurement yet, but this is how a quantum computer derives its power. Okay, so how do we take advantage of this? Well, we need algorithms, of course. And many of the algorithms that we know today were developed by my colleagues here, whose pictures I show at the bottom here at MIT. MIT was foundational in making this happen. I won't read through the whole slide, but the first column of algorithm shows the major categories where we know quantum will make a difference. Simulating quantum systems. Factoring. That's basically mathematics that lies behind a lot of our encryption schemes. Linear algebra. Anyone who's an engineer or an econometrist or everybody uses linear algebra. Optimization. Searching unsorted databases. This is where quantum computers will outperform classical computers when we can build one at a large enough scale. Okay. So how do we realize that? And we'll call it commercial quantum advantage. Quantum advantage would be my quantum computer does something better than a classical computer for a problem that I don't know how to commercialize. Commercial quantum advantage is doing that for something I do know how to commercialize. And so first off, there better be no fast classical algorithm. If I know a good classical algorithm, I should just use those fantastic GPUs that we've already got to do it, right? They're fantastic machines. If I know how to do it efficiently on a conventional computer, use a conventional computer. But there are many problems where I don't know how to do that. Okay, number one. Number two, okay, now I need to figure out a good quantum algorithm that will solve that problem. There are lots of problems I'm aware of today where I don't know how to do it on a classical computer, and I also don't yet know how to do it on a quantum computer. And I often say that we need more people thinking about the application space and writing those algorithms. That's a major part of what we do in the Center for Quantum Engineering, is work with companies to figure out an algorithm that's going to affect your bottom line. Okay, so then the third one is it should be a useful problem. There have been many demonstrations of quantum advantage over the years that are not commercial quantum advantage because although they prove the point, quantum computers can outperform classical computers, we don't know how to commercialize it, and therefore we don't know how to monetize it. If we look at this current overlap, it's actually pretty small. It's increasing in size, but it's small. There's a lot of research going on here. And again, I emphasize that this is the major task in addition to building the hardware. Now, once we have a problem, there are a couple types of advantage that we can gain from a quantum computer. The first, well, before I get into the first one, basically what we're talking about is how big a system, how big a computer do I need? Or what's the time to get to a solution? Or how much energy do I need to get to a solution, right? All of these are important. It's not just the speed, right? And that's proportional to two factors. One is a polynomial in the size of the computer, and the other is exponential in the size of the computer. Now, the polynomial one is an improvement that a quantum computer can make. For example, if it took something that goes as n and made it square root of n, that's a big improvement, especially if n is a big number, right? Time, million years, take the square root. Okay, 1,000 years, that's a big improvement. But that pales in comparison to exponential improvement. An exponential improvement means n is upstairs and it comes downstairs. Okay, and we don't really experience exponential growth in our everyday lives. And so to give an example of exponential growth, let's imagine the following. We're going to use a classical computer, supercomputer, let's say, to simulate a quantum computer, to do what a quantum computer can do. And you could ask, how much memory will I need to store this quantum state that I told you about that contains 2 to the n components? So if I have 30 qubits, that's 2 to the 30th power. You can do that with a conventional laptop. Okay, I can store that in. It takes a lot of memory, but I can do it. If I just increase it by 20 more qubits, now we have 50 qubits, I need the top 100 supercomputer in the world, maybe even the top 1. If I go to just 80 qubits, now we start to get into a fantasy where I need to somehow network all of the computers in the world and use all of their memory just to store this quantum state. Double that to 160, you can go to Wikipedia, 2 to the 160th power is an estimate for how many silicon atoms we have on Earth. And I would need to employ each one as a memory element. And now 10 times where we started at 300 qubits, I now need all of the atoms in the known universe and employ each of them to be a bit of my memory, okay, to store this massive state. Now, okay, that's exponential growth, right? It's almost unbelievable. Of course, the challenge is utilizing it for commercial quantum advantage. So why don't we have quantum computers right now at large scale? It comes down to two times. One is the coherence time, and one is the gate time. So let's take them one at a time. So the coherence time is how long qubits remain quantum mechanical. I can start at, say, time t equals 0. I've set up my computer and I let it run. And I'm running my algorithm on it. But as I'm doing that, everything else in that computer's environment is creating noise and conspiring against me to take those qubits to a different place. And so these environmental disruptions over time, you can think of it as blurring the quantum state, and eventually it's lost. Now, the qubits didn't disappear. They're still there. But the state that they ended up in, which is the answer to my problem, and I'm trying to go from point A to point B, on the way there, the noise is taking me to some other point C, and I get a wrong answer. Right? The time frame over which that happens is called the coherence time. Second time is called the gate time. That's basically, I have an algorithm, it has a large number of steps. How long does it take me to do each step? Right? And the figure of merit then is how many steps can I take before this environment overcomes my quantum computer, right? With that, we can start thinking about different types of qubit platforms and modalities. There are lots of candidate technologies, and I won't talk in too much detail about them individually, but what I want to show is how they compare to one another on this chart. The left vertical axis is how many steps I can take before things fall apart. And the right axis is basically 1-to-1 in that we call it fidelity. So one error in 100 gates is 99%. One error in 1,000, 99.9%, et cetera. So you want as high a fidelity as possible. The horizontal axis is just the gate speed. How fast can I take those steps in hertz? You know, think of it as your computer's clock speed. So the upper right corner is where the best performance is. And some of the major players today, one is called a trapped ion. That's a natural atom. It's held in space, and operations are performed on it. They have decent fidelities. They're trying to go faster. I work on superconducting qubits. We're pretty fast. We want higher fidelity, right? That's what we're working on. Neutral atoms, another up-and-coming technology. They're sort of in between, right? So there's no clear winner right now. And if I think about the history of classical electronic computing, there won't be a winner necessarily. We started with vacuum tubes. We went to bipolar junction transistors. That became too power hungry. We went to emitter coupled logic. That became too power hungry. We went to CMOS, right? We then, you know, the Dennard scaling ended. Moore's law ended. So what did we do? Well, we went to GPUs. We 3D integrated, right? Heterogeneous integration, right? Quantum computing very likely will evolve in the same or a similar way. Okay. Just to show that there's so many different modalities here, superconducting trapped ion, photonics, silicon, et cetera, and all the companies that are trying to do that, many of them are blue chips. A lot of them are startups. One of them, Atlantic Quantum under the superconducting, is a startup that spun out of my group here. And we're all trying to commercialize this technology, make it commercializable. This is what quantum computers look like today. On the lower left is IBM's Osprey. This is about a 430-ish qubit machine. You can see that it's 3D integrated. That 3D integration technology developed here at MIT and Lincoln Lab. In the upper left, Google's Willow chip. This is 100 qubits, but last fall they demonstrated quantum error correction scaling for the first time. Major demonstration. I'll show that in just a moment. Upper middle is QEra's Aquila. That is a neutral atom quantum computer, and it spun out of Harvard and MIT. Quantinuum, that's a trapped ion. The lower right, D-Wave, that's a quantum annealer. And in the bottom middle, of course, that's not a quantum computer. You'll recognize that as the right flyer. Wasn't the first time humankind flown. We often say that, but it's not true. We had hot air balloons, okay? We had gliders, aerodromes, right? But what did this event show? It was the first time that it all came together, that you got a person on board, self-propelled, it took off, it landed. And I put this picture here because I think that all of these technologies that you're looking at, they're basically at this level of development. It's very early days. But we look back at that Wright Flyer and we say that was the dawn of commercial aviation because that's when it all came together. And as I look at these quantum technologies, okay, my opinion, but I look at these quantum technologies and I think, yeah, we're at the dawn of commercial quantum computing. It's going to happen. It may take 10 or 20 or 30 years, but it is coming. Okay, so there's a lot of promise, but to realize that promise, we need to engineer systems that are much larger than this. They have to be robust. Okay, we'd like to have a fuselage on the plane and put some seats, have some people in the front, right? We need to do the equivalent of that for quantum computers. Okay, and one of the biggest challenges we face, a grand challenge, is called quantum error correction. These qubits are quantum mechanical and they're faulty, and they fall apart after, say, 1,000 or 10,000 operations. You could then ask, that's what's in the yellow, by the way. We call them physical qubits. They're the physical embodiment of a qubit. You could ask, what do you need for commercial advantage? How many operations? Probably 1 billion to 1 trillion operations. So we can do about 1,000, and you need to be at 1 billion or 1 trillion. So how are you going to get from where we are today to that? Well, my students work very hard at improving qubits. We've been doing that for years, and we'll continue to do that, but I don't think we're going to make up a factor million with material science, right? Fortunately, we don't have to do that. Thanks to Peter Shor and his colleagues, we know how to do quantum error correction, and that's how we're going to get beyond this gap. By the way, transistors, why are they ubiquitous? Because they're almost perfect. The error rate of a transistor is 1 part in 10 to the 20th power. Right, almost never fails. If this crashes right now, almost certainly the software, not the hardware. Fortunately, we don't have to be there. We just need to be in the blue region. And the concept of error correction is something we're all familiar with. We form teams. That's basically it. Rather than using 1 qubit to encode the information, we're going to form a team of qubits. In this case, 9 qubits. You can see the yellow ones. There are 9 of them on the right. And we call that a logical qubit. It represents 1 qubit's worth of information, but it has 9 physical qubits to do it. And the classical version of this is majority voting. You basically ask, how many of you think I'm in state 0 versus how many think I'm state 1, and you majority vote. And so that's the concept. You'll also see some blue ones there. Those blue ones are basically the referees. They got a yellow card and a red card. In fact, they have 3 cards in this game. And when one of their neighbors has an error, they're going to throw up a flag. And me, as the operator at room temperature, is going to look at that flag and say, one of the neighbors has an error. And by looking at all of the referees and the errors they flag, I can determine which physical qubit had an error, and I can go back and fix it. This is almost magic. It's not magic, but it's amazing. What's amazing about it is we all learn that I can never measure the physical qubits. If I do, I destroy the quantum information. I make them classical. But I never measure a qubit. I just measure those referees, right? And that's how I protect quantum information. Now, of course, none of this comes for free. If you look at the error rate of the logical qubit, it goes as this formula. There's a C. C stands for cost. It's not free. If you form a team, of course, it's not as easy as just having 1 person there, right? We know this in companies, right? Google has 150,000 employees, right? And they're not all working on the internet or AI. You got an HR department, you've got a security department, et cetera, et cetera, et cetera. But you still do it because we know that by forming teams that are focused on the product and all of the stuff and the cost that goes around it, it still provides advantage, right? That's the concept of a logical qubit. And as you make the team bigger and bigger, it becomes more and more performant. How much more performant? Exponentially so. What we're seeing on the right here, the vertical axis is the logical error. That's the error rate of the logical qubit on a log scale. The vertical axis is the error rate of the individual qubits. And that's not on a log scale. So 1 in 1,000 is just to the left of 0.15%. That's basically where we're at now. And you could ask then, how does this scale with the size of the team? Well, that's the different colors. Distance 3 is jargon, but it means 17 qubits. Distance 5 is 49 qubits, etc. If I go from 17 to 49 qubits, I get this improvement here. Lambda is the what we call it, but from distance 3 to distance 5. If I go to one size larger, distance 7, my error rate goes down. And notice each time it goes down by about a factor 10. I can keep doing that. I just keep making the team bigger and bigger and bigger and bigger and bigger and bigger. And eventually I just make it big enough that I achieve the error rate that I want. And here we are down at 1 part in a billion. You could ask, okay, distance 17, that sounds like a big team. How big is that team? 577 qubits. So I increased from 1 by a factor 577, and my error rate went down by a factor 1 million. Exponential growth again, right? This is how we're going to overcome these errors. The demonstration last fall from Google is shown here. And what you're looking at is the logical error rate versus how many times they did the error correction, the error detection. And in red is the distance 3 curve. And when they went to distance 5, they added more qubits. It goes down to the teal curve. They go to distance 7, it goes down to the dark blue curve. Down is better, less error per cycle. And in fact, if you look at this just above the teal, I think it's in green, that's the best physical qubit. That's the best team member. There's always a best one on your soccer team, the one who's the star. This is the star qubit. And the team at distance 5 was already better than the best star on the team. And of course, distance 7, even better still, right? This is common sense, right? We know that forming teams will always, if they're good, they will always outperform any individual on the team. So Google Quantum AI demonstrated this last fall. This will be remembered for decades. It's a major demonstration. It shows that we can achieve quantum resilience. Now, many of you may have seen this in January. Of course, this is Jensen Huang, and he's being interviewed. And he was asked, when are we going to have a quantum computer? And he said, well, 15 years seems a little early, 30 years, that seems a little long. I think most of us would agree 20 years. And of course, all the stocks tanked from the quantum computing companies that had IPO'd. And come back in June, and he was like, okay, wait a minute. What I meant to say was that we're actually reaching an inflection point. I think these two things are equivalent. Basically, when Jensen was asked, when are we going to have a quantum computer? He's thinking, when are we going to have the quantum computer that's fully performant and it's going to help me design new pharmaceutical drugs, right? He's thinking of the end game, and he said 20 years. I thought that was fantastic. A lot of people complain, oh, Jensen, you're killing the industry. No way. We have to my mind, one of the smartest engineers in industry today saying we are going to have the end game quantum computer in 20 years. That's fantastic, from my mind. Stocks all recovered, by the way, since then, so and more if you follow it. I just want to say that we have this industry engagement group here at MIT. If you'd like to learn more, feel free to contact me. A number of companies involved. We also do a lot of entrepreneurship here at MIT. I mentioned Atlantic Quantum, my own company, but and also QEra, the neutral atom company. Labor Quantum spun out of my group a couple years ago. That's a software company. Anyways, lots of companies are spinning out of MIT as well. And again, if you'd like to learn more about what's happening in the industrial space in quantum, feel free to contact me. So today's reality, and this is, I think, the last slide. One, quantum computers will not replace conventional classical computers, right? Quantum computers solve certain problems really well, but they're not going to do Microsoft Word. For a lot of these applications, they're no better than a classical computer. They can do it, but why would you go to the trouble when we've got really good classical computers already? We need more quantum algorithms. We talked about that already. But one of our main jobs going forward is to find commercially viable applications. RSA sounds scary that quantum computers can break it, and we got to pay attention, but it's not going to happen today. To break RSA encryption, public key crypto systems, is going to require a very large error-corrected quantum computer with millions of qubits. That's still a ways away. But we need to switch over to a new crypto system now. Post-quantum crypto. NIST announced it last year. goes by names like Kyber. Okay. Why do we need to do that? For forward security. There's information that we are encrypting today that we want to retain security over, not just today, but in 10 years, 20 years, 30 years, right? And at some point, we will have a quantum computer that can decrypt everything that we're storing on hard drives today. Okay. And we will need quantum error correction to make this possible. And I think with the demonstration from Google last fall, we saw a major step in that direction. And so with that, I'd like to thank you for your attention.
Any question? Questions for Will?
Hey, thank you, Will.
Yeah.
I wanted to ask, we were chatting just before, when you envision where these quantum computers are going. I'm Bruce Heck, by the way, from Mithril Technologies, and data center day. So what, paint a picture for us in 20 years when these first workable quantum computers are in practice, where will they be? And how will, another question that came up this morning in conversation is cities. You know, if cities got changed by the automobile and they got changed by the introduction of the airport, as you said, commercial aviation,
Yeah.
what does the future of, and maybe not just today's data centers, but that 20-year trajectory from today to quantum computers, what does this mean for us as humans and the future of our cities?
Yeah, so first part is that quantum computers absolutely, as far as I can tell, need to run in tandem with a very large classical computer, right? And so our data centers will have, of course, the classical racks that we all know today, but next to them will be quantum computers, because the quantum computers that are doing this error correction, they need those classical compute and that classical compute power just to interpret what the referees are telling us where the errors occur. So, and plus, some of these computers are very cold, and if I am writing an algorithm, I want to do that at room temperature on a classical computer. And so for very practical reasons, quantum computers will always run in tandem with conventional classical computers. And in fact, many of the algorithms will leverage that classical computer as well. So a part of that algorithm may run on the classical data center computer, but then it gets to a hard part, and then it's going to hand that off to the accelerator. The quantum computer gets the answer back. So it's, and the future, I don't have a crystal ball, of course, but there are some pretty thorny problems facing humankind today. And energy is a big one. Climate change is another one. We're living through this now, right? Do we abandon fossil fuels, knowing that that's going to wreck the economy so that we can have a cleaner future? Or do we buy ourselves some time so that we can find solutions to this problem and then implement them? I don't have the answers, but I think that one step towards this is quantum computers, because where they really shine is in simulating quantum chemistries, so better batteries, quantum materials, better materials, and engineers can use this information then to develop the technologies that hopefully will allow us to live in a cleaner environment.
Great. All right. Thank you, Will.
Okay, thank you.
Terrific.